You can start.
Shall I begin?
Yes.
Okay. Well, welcome everyone. Thank you so much for joining us here. The Moon Rocks webinar was organized by the Cultural Considerations Working Group in association with the Moon Village Association. I'm Lisa Pettibone, and my colleagues and I, Remo Rapetti and Arthur Wood, who are co-chairs of the group, research topics for webinars that relate to the cultural aspects of our relationship with the moon, which will be crucial in future settlements there. Earth's satellite is a physical and emotional part of our existence, giving up its mystery slowly over millennia, and more recently in the rocks collected there by the Apollo moon missions. Examining moon materials not only connects us with the facts of its creation, but also our wider curiosity and need to explore the cosmos that embraces us. In his book, Myths to Live By, Joseph Campbell said, "For although our voyage is to be onward, it's also to be inward, to the sources of all great acts, which are not out there, but in here, in all of us, where the muses dwell." So it's with great pleasure that we welcome Erika Blumenfeld and Ian Crawford today to bring us closer to an understanding of the moon in all its guises. Erika is an artist and researcher who established NASA's Astromaterials 3D, a virtual library of moon rocks and meteorites. She is part of NASA's OSIRIS-REx team examining the recent return of materials from asteroid Bennu. And currently, an Emerson Collective Fellow, her project Earthlight will ponder the poetic and chemical imprint of Earth's light from space. Ian Crawford is an astronomer turned planetary scientist and is currently professor of planetary science and astrobiology at Birkbeck College, University of London. The main focus of his research is in the area of lunar exploration, including the remote sensing of lunar surface and the laboratory analysis of lunar samples. He has research interests in the field of astrobiology and the future of space exploration, which he believes will become increasingly important for the future of humanity. Before we just get started, the webinar will be recorded or is being recorded now, and you can ask questions in the chat window. Okay, so Erika, can we invite you to share your screen, please?
Yes, let me just get settled here. Okay, can you see my first slide?
Yes.
Yes.
Okay, great. All right, let me just rearrange some things here. Great. So thank you so much, Lisa, for that very warm welcome, and thank you to the Moon Village Association for the invitation. So my presentation is going to be about 20 minutes, and I thought I would take the first half to talk a little bit about my artistic practice and illuminate how the art-science intersections in my work eventually led me to the Astromaterials 3D project. And then I'll take you on a quick journey through the Astromaterials website and explore application. So while I've been captivated by our closest luminary for as long as I can remember, and early artworks included many lunar references, my own journey with the moon as a subject in my work began in 2003, when I became interested in capturing the light of the moon as it changes throughout lunar cycles and various lunar phenomena as part of my body of work called Light Recordings. Light Recordings are a series I began in 1998 in which I distill photography down to its most basic components, light and light-sensitive materials, and build my own lensless recording devices in order to document the phenomena of light across various atmospheric conditions and astronomical cycles, such as solstices and eclipses and the sun's daily shifting through the season, seasons, all to visually chronicle the recorded light over time. And initially I recorded the light of the sun, but in 2003, I became interested in recording the light of the moon. From September 2003 through September 2004, I documented every full moon in order to track the subtle variances in moonlight intensity month to month, and to record how moonlight is affected by the subtle shifts in atmospheric conditions. In this piece, Light Recording Greatest Apogee Perigee of 2004, I documented the period during the moon's elliptical rotation around the Earth when the moon is at its closest and its farthest away from Earth over consecutive new and full moons, respectively. So the farthest, darkest new moon and the closest, brightest full moon. This piece recorded the amount of moonlight during each of those 15 nights between that year's most extreme apogee-perigee cycle. In Light Recording Total Lunar Eclipse, I documented the entire 4 hours of the diminishing and reappearing light of the full moon while it was being eclipsed by the Earth's shadow during the total lunar eclipse of October 27th, 2004, which was recorded in the very dark skies of the Galisteo Basin in New Mexico. I exposed a separate piece of film every 7 minutes during the eclipse and then configured them chronologically from left to right, top to bottom. During a 2-month residency at the McDonald Observatory in the autumn of 2004, I produced my first video work to document lunation cycle 1011. A lunation is the mean time between 2 successive new moons, and the lunation numbering system is calculated from the first new moon that occurred in 1923. I created the piece using an altered telescope and self-built lensless camera devices, where the varying intensities of light radiating from the moon were recorded onto handheld photographic film. The resulting images portray not only the quantity of moonlight, the changing quantity of moonlight in its nightly phase, but also my own hand, in which free holding each piece of film over the long 2-minute exposures moved very slightly. This piece captured the relationship between technology and the human implementing it, and is additionally, and this is additionally expressed in the completed piece, where each of the exposures that I took over those 30 days were then animated in sequence to the speed of my own heartbeat to produce a moving account of the lunar cycle that is both human and planetary. It was really at this time that I began developing a research-based art practice in collaboration with the sciences. I found that I could push the boundaries of my own creative imagination by investigating an idea from inside another field. By adopting a somewhat scientific methodology in my artistic process, I have followed a rather non-traditional studio practice. I've sought studios in laboratories, observatories, and in remote landscapes. My creative inquiries have increasingly led me to work alongside scientific and research institutions in order to bring both fields of knowledge into a conversation. I like to think of myself as both a curiosity seeker and a collector of questions. Each of my projects can be tethered back to an initial inquiry where I investigate the places where our phenomenological world meets the human experience of wonder and meaning. My inquiries are centered on the places where art, science, nature, and culture converge. I'm most interested in the questions that lead to where humanity finds meaning in our relationship, our sense of belonging to the natural world. One of the responsibilities I feel artistic knowledge has when in collaboration with scientific knowledge is to nurture and defend the important role that meaning has in the search for the understanding the mechanisms of our world. I'm interested in investigating the places where art, and science each source and create meaning, and look for the places where the stories of our cosmic connections begin to unfold. I've been picking up interesting rocks along shorelines and mountain paths since I was small, always sensing the mysteries held within them. In 2011, my long-standing love of rocks was intensified during an artist-in-residence sailing expedition with Cape Farewell a UK arts organization that is interested in climate change and cultural studies, where we sailed around the Scottish Islands. There, I encountered the majestic basalt pillars and Louisian gneiss the region is known for, in inspiring me to deepen my knowledge of geologic and planetary processes. Ask any geologist about the processes they study, and they will nearly always end their explanation with this same mind-dazzling statement that the story itself is written in the rock. So my work as a whole intends to study the notion of an embodied relationship with the cosmos, that we are, in our very chemistry, of and from the stars, an idea that, although has been pondered for centuries, has been proven within my lifetime. So it is exactly this link with the evolution of star matter and the elements of our universe, the stuff and stories of cosmic processes, that led to my interest in rocks from space and to the Astromaterials 3D project. I like to think of rocks as scrolls of knowledge passed down through the cosmic, planetary, and geologic ages that tell the story of primordial formation. In picking up a rock, we gaze into its complex structure to know something of its secrets, awaiting its tome of cosmic riddles to unravel. If one knows the language written in the stone, the answers begin to emerge. At that point, a persistent question arose for me. Might it be possible to hold a rock in one's hand that tells the story of the whole cosmos? While this question is poetic in nature, it is also true that rocks from space collectively tell the story of how our solar system evolved. My inquiry into how far back in time the story of a rock might be able to take me eventually sparked an idea, leading me to contact NASA in January 2013 to propose the Astromaterials 3D project. To my amazement, they were interested, and I began working on the project with an incredible team at the Astromaterials Research and Exploration Science Division, known as ARES, at NASA's Johnson Space Center. A little over a year later, my team and I had produced the first ever 3D model of a moon rock, when we were then awarded a NASA research grant to pursue the production of the Astromaterials 3D project. NASA's Astromaterials Acquisition and Curation Office, which is part of the ARES division, houses NASA's collection of extraterrestrial samples. These collections include samples from the moon, asteroids, comets, solar wind, and the planet Mars. Being both scientifically and culturally significant, the samples require a unique conservation approach. Government mandate dictates that NASA's Astromaterials Acquisition and Curation Office develop and maintain protocols of, quote, documentation, preservation, preparation, and distribution of samples for research, education, and public outreach for both current and future collections of astromaterials. This is where Astromaterials 3D felt we could modernize these concerns and requests. So how did we create it? Our first step is to take high-resolution precision photography, which we call HRPP. NASA's astromaterials are housed in a multi-cleanroom facility and have strict curation protocols to protect them for research and posterity. Therefore, the rocks must be kept inside a nitrogen cabinet at all times during my photographic process. There are also restrictions on what kinds of materials the rocks can come in contact with. And actually there's three. It's Teflon, stainless steel, and certain types of aluminum are allowed in the cabinet. So therefore, we could not put a 3D imaging scanner inside the nitrogen cabinet to scan the rocks, as that equipment contains materials that do not meet curation protocols. So instead, I had to develop a method to manually photograph the rocks through the glass, through the small windows of scientific glass that exist on one end of the cabinet. Using a custom imaging setup, I capture images in increments of 7.5 to 15 degrees in rotation and at 15-degree elevations on both hemispheres of the rock, which totals about 240 to 480 photographs for each sample. I use high-resolution professional camera systems that range from 60 to 100 megapixels in order to maximize the surface detail and to achieve a final model texture that is what I like to think of as research grade. The technique provides images that are achieve resolutions as fine as 30 to 60 microns, depending on sample size and camera system implemented. The method provides exceptional detail and reliable fidelity of the rock, meant to meet the quality demands of both today's and future users. We then use Structure from Motion software to produce our 3D reconstruction of the HRPP images using photogrammetric principles. The method uses image processing algorithms and techniques originating in computer vision to resolve 3D models for accurate and detailed visualization of each sample. The software provides a stepwise process that then we manually tailor for each model based on the unique spatial and specular reflectance properties of each rock. Additionally, each of the rocks in Astromaterials 3D project are XCT scanned at either the University of Texas high-resolution X-ray computed tomography facility or at the new Astromaterials Research and Exploration Science CT laboratory at NASA Johnson Space Center. XCT image data provide a complete one-to-one volume data set of the rock, where the brightness variation of textural features is related to both density and composition. So we start to get a sense of what the rock is made of. And these are the images that you see inside the rock when you slice through on the Astromaterials 3D Explorer application. Finally, the process for registering the coordinate system and combining the SFM model with the XCT data in order to achieve what we like to think of as the fused 3D model of both data sets went through several stages of development before we found the final method, which is the Astromaterials 3D Explorer. And that fuses the models through a custom engineered browser-based software application that ingests the exterior and interior image data and digitally fuses them into a single object. The Explorer application uses a combination of sprite graphics in the browser canvas and on-demand high-resolution downloads. The data is rendered in real time within the user's browser using a Three.js 3D library on a WebGL platform. This technology enables our high-performance, hardware-accelerated 3D visualizations, providing high-fidelity data that is streamed on demand and produces a very high-quality sample visualization at the lowest possible bandwidth and computer processing power. So bear with me. I'm going to take a sec to set us up, and I'm going to take you over to the Astromaterials website. Arranging some things here for a sec. Okay, can you see the screen at this point then?
Yes.
Okay, great, thank you. Okay, so welcome to Astromaterials 3D. If you haven't been here before, I'm going to take you on a little ride, and if you have, I hope you'll follow along and enjoy this little demo. Right from the very start, we wanted people to get a sense of being able to interact with the samples and have it be a more visceral experience. So you can interact with the models right from the homepage, and then it's sort of a choose your own adventure. Right now we have the Apollo Lunar Collection and the Antarctic Meteorite Collection. Soon we will have the OSIRIS-REx collection and other collections, Hayabusa 2 and some others as well. Today we're going to focus obviously on the Apollo collection, so I'm going to head over there. And we really wanted to create an experience of a visual storytelling through the website itself, where through each of the layers of the website, you go deeper and deeper into the story of the rocks. So here we have a visualization to show you where each of the 6 Apollo surface missions were, and then you can enter into the gallery for each of the sample collections to see the rocks that we have available from each mission. So I'm going to jump over to Apollo 16 and show you one of my favorite rocks. This was the very first moon rock ever to be made into a 3D model. So it's a team favorite, and we're very proud of this. It's one of the highest resolution samples that we have in the collection. Again, you can immediately start to play with the 3D model right from the sample details page. This page is also where you can find the every rock tells a story, where I write little biographies based on the scientific and cultural stories of the rocks. We also include a little video of the CT data, so you can view this on smart devices. The Explorer is too process heavy, and it won't operate on a phone or and some tablets. So we wanted everybody to be able to see the interior from whatever device they have. So this is for that. This is where you can also download all of our data freely. It's both the full resolution and the low resolution models, and the XCT imagery as well. And if you want further information about the rock, you can head to the sample curation page, which is part of another website. And so the real heart of Astromaterials 3D is the Explorer application, which I was describing. And this is really where you have incredible capability to see the detail of the rock and the reconstructions. You know, zooming in and seeing this incredible glassy crust and this anorthosite clast gives people a visceral experience of what's happening on the lunar surface. And of course, you have this console here, which allows you to see the processing details, thread back to the details page if you need to. But we include all of our processing details for those of you who are interested. This is where you also can slice into the rock. So if I start slicing, you can see the slice plane there on the left. And if I rotate around, you'll get to see this beautiful basalt clast that's in there. And yeah, one of the few, actually. Anyway, so and you can do things like, you know, if you want to go slice by slice, you can incrementally go through. You can take a picture and it will pull up the actual full resolution slice of that exact slice in the stack of the CT scan. I'm going to head out here for a minute and show you. This is a way to view in different directions the XYZ from the scan. If you want to jump to different planes, you can also nudge the rock in different directions if you need to. We also have a spotlight to change the luminance on the rock, and this is particularly interesting, particularly on some of the meteorites, where you can see some of the details in the fusion crust. But you get a really interesting sense of angularity here on those surface characteristics. So if you can also view in anaglyph if you have 3D glasses at home.
Mm-hmm.
This is really fun, and particularly when you start zooming in and it looks like it's coming out at you. And then scale guide, if you're interested in the actual dimensions of the rocks, this is right to the bounding box of the 3D model. So it's the one-to-one volumetric data from the CT scan. So that is an accurate size. And then we have this, which is a new feature, NASA curated pins, where we worked with some of the scientists to find regions of interest on the rock for people to start to learn who aren't already familiar with planetary, you know, the science. So, for example, you can turn on these pins, and it will give you a little explanation. Again, this large clast, and then the interior. So each of the samples has some of these, and you can create your own pins too. Add a pin and write a note to a friend, and we're having a little issue. Anyway, you add a pin and it gives you a place where you can write notes, and then you can save and share and send it to colleagues or share it in other ways. Okay, I am going to jump back here. There's some other sections. We have the About section and the Technology section. You can learn about the team. I like to think of this as our movie credits, because there was an enormous number of humans and great minds and creative ideas that went into this project. And then one of our new areas is this publications, where we highlight science papers that are using our data or that our team members have been involved in, educational and outreach and engagement efforts that are being where the models and the website are being used in NASA education. And then also we've been highlighting artists who have been using the materials for art making, and you can look here and see the publications if you're interested. So I'm going to head back here for a minute. I think I have a few minutes. I'm going to pull up 60025 and let you enjoy this view of it while I read the Every Rock Tells a Story. And I thought I would end with this, sort of end with how I began, with the light of the moon and the story of this rock, this tiny piece of the moon that taught me over hours and hours and hours of trying to illuminate it for the photography. And yes, lighting rocks through a glass into a glass cabinet where everything is a reflected surface, and when the rock is very whitish in color is a challenge. And through that process, this rock really taught me why the moon glows the way it does. And so I thought I would read this story, and then I will end. Lunar sample 60025 is truly an elder amongst the Apollo lunar sample collection. Classified as a Faroan anorthosite and dated to be around 4.4 billion years old, it is one of the oldest rocks brought back from the moon. 60025 was collected during the Apollo 16 surface mission, which intended to study both the Descartes and Cayley formations, and was found just 15 meters from the lunar module. The formation story of this incredible piece of our moon is as wondrous as it is ancient. When you look up at the moon at night, the highlands are the lighter illuminated areas you see on the lunar surface, and they are compositionally different than the larger, darker areas that you see, which are the mare basins. The highlands are a much older feature and primarily anorthositic in composition, anorthite plagioclase being one of the primary minerals to have crystallized out of the magma ocean that covered the moon in its infancy. Being less dense than the magma, this light-colored mineral floated to the top of the magma ocean, forming the moon's first crust around 4.4 billion years ago. This rock is a piece of this first crust. The Faroan anorthosite suite of Apollo lunar samples, which includes plutonic rock 60025, has provided significant understanding of the chronology of the lunar crust formation, and many studies have included this moon rock in assessing the timeline. Most of the plutonic rocks that formed from ancient lunar magmatism in the Apollo collection were crystallized directly out of the fledgling moon's magma ocean, which itself formed through the moon's cataclysmic impact origin. Lunar sample 60025 also tells the story of continued impacts on the lunar surface. While most of the large impact events can be dated between 3.5 and 4.1 billion years ago, the impact event that originally excavated 60025 from its depths is thought to have occurred much earlier, at 4.3 billion years ago, indicating that large impact events may have been occurring during the moon's earliest formation. 60025 became re-emplaced within the lunar crust after its initial ejection from the ancient impact event, but was freed again by another impact in its more recent history. Cosmogenic dating indicates that this rock lay thereafter on the lunar surface for about 2 million years before being picked up by Apollo 16 astronauts. Thank you very much.
Thank you, Erika. That's fantastic. Wonderful to have in-person tour of the lovely site. I really have enjoyed digging around in it myself. So this makes me want to go back and do more.
Yeah. Thank you.
Great. So, Ian, can we invite you to share your screen now? Great. Is your audio on, Ian?
Sorry, it is now.
Yep.
Can I just ask whether you can, what you can see?
We're seeing the slides run alongside and then a main image. But there we go. That's showing the main image now.
Okay. All right. Well, okay. Can I just check the time? Do I still have 20 minutes?
Yes.
Okay. Right. Thank you. So, yes, welcome everybody. So my name's Ian Crawford, and I'm a planetary scientist, and I guess I've been asked to talk about some of the science that we've learned from the lunar samples. So I will do my best. So I'll start with this rather nice image here. This is from Apollo 15, and it shows the Apollo 15 astronaut James Irwin preparing the lunar roving vehicle, aka the moon buggy, for its first traverse in 1971. I just draw attention to the fact that the fact that the last three Apollo missions, 15, 16, and 17, had this vehicle with them greatly extended the range at which the astronauts could travel, and therefore the diversity of geological materials that they could collect. And so I just draw your attention to the back of this vehicle, which has these plastic bags, are the sample bags, into which the rock samples were collected and then eventually returned to the Earth. So Lisa showed the landing sites of the Apollo missions, and I just thought I would draw your attention to the fact that there've been 10. So there were 6 successful Apollo landings, of course, but now we've got rock and soil samples collected from 10 localities on the moon, and I've plotted them all here. So these were the 6 Apollo landing sites, then the 3 robotic sample return missions performed by the Soviet Union in the early 1970s, Lunar 16, 20, and 24, out here on the eastern part of the near side. And then in December 2020, China's Chang'e 5 sample return mission, which collected samples from that locality up there. But I just want to draw your attention to the fact that although it's great to have samples from these 10 locations, if you look at them, they're all on the near side. So this is the near side of the moon. This is the far side on the other side. No samples returned from the far side at all yet. And if you were to draw a sort of contour around these locations, with the exception of Chang'e 5, they're all pretty close to the moon's equator on the near side. And so currently we've got no samples at all from high latitudes on the near side, or even very far out in the western part of the near side, and nothing at all from the lunar far side. So when we talk about lunar samples, it's important to realize that our knowledge is still pretty incomplete. There is still a great deal of the moon that we haven't sampled yet, and that is, of course, a very strong argument for going back to the moon and collecting more samples from more places. Anyway, I thought I would briefly summarize the scientific legacy of the lunar sample collection, which is dominated by the Apollo collection, but supplemented by the lunar and Changi 5 samples. So these bullet points list some of these information we've obtained from lunar samples, and I'll just in the following few slides just go through some of them. Obviously, by having access to lunar materials, we've learned a great deal about the geology of the moon itself as a planetary body, its history, and its early geological evolution, which bears, of course, on the early evolution of the Earth-Moon system, because the moon has been connected to the Earth since its beginning, and therefore the early history of the Earth itself. And these pictures are kind of just illustrative. This is an Apollo 16 breccia, not dissimilar from the some of the rocks that Lisa's just shown you, but I've just got it here as an example of a lunar sample. The picture at the bottom shows these dark grains are Apollo 12 soil samples, and these are dark basaltic lavas, which we're working on, or have been working on at Birkbeck College, and myself and two of my colleagues at the Johnson Space Centre collecting these samples for our study of Apollo 12 basaltic samples. But really, these pictures are just here to sort of show some lunar materials. So studying these lunar samples have told us a great deal about the moon itself. They've also enabled us to determine the rate at which meteorites and asteroids have been striking the lunar surface, which turns out to be very important for planetary science. It sounds rather prosaic. I've called it here calibration of the inner solar system cratering rate. But without these samples, we wouldn't have a knowledge of when the rate at which meteorites had been striking the surface of the moon, obviously. But then that is also the rate at which meteorites have been striking the Earth. And it's used with various assumptions to estimate the rate at which meteorites are striking the bodies of all the planets in the inner solar system. So this actually turns out to be quite an important scientific legacy of Apollo. We've learned from the Apollo samples, particularly the Apollo soil samples, like these Apollo 12 soils here, that have been sat on the surface of the moon for, well, various lengths of time, but often billions of years. And during that time, they've become they've retained a record of things falling onto the lunar surface from above. And these include the solar wind and cosmic rays that come in from the galaxy. So there's a record here in the lunar near surface environment of the activity of the sun and the galaxy through time. I'll return to that if I have time. And then finally, there are insights into the origin of the moon itself, which is crucially important to the origin of the Earth-Moon system. So in terms of lunar geology, I think I'd like to stress how efficient the Apollo astronauts were as field geologists. And given that each Apollo mission was only on the surface for about 3 days, and 2 astronauts operating in really very challenging circumstances, turned out to be hugely efficient as geological field scientists in terms of the quantity of rocks collected and returned, but also their diversity. And many of these samples were judiciously chosen by astronauts making geological decisions while on location on the moon. And this really did demonstrate the efficiency of Apollo as a geological, the geological benefits of the Apollo program. So this site shows the Apollo 17 landing site, the Taurus-Littrow Valley. And the Taurus-Littrow Valley is about 8 kilometers across, and it's flooded by mare basalts. These are lavas erupted from the interior of the moon. And it's bounded by these large kilometer-high mountains that around the Apollo 17 landing site were given these names based on their relative location to the landing site. So we have the South Massif, the North Massif, etc. And the Apollo 17 lunar module, if I just get my pointer back, Apollo 17 lunar module landed here in the middle of the Taurus-Littrow Valley. And then these lines show the traverses made by the Apollo 17 astronauts on their lunar roving vehicle, and in 3 days that you can see they span from one side to the other of this valley, which is 8 kilometers wide. and collected a wide diversity of different rock types, rocks and soils, some of which are illustrated on the panel to the right, and also, not to be forgotten, deployed a wide range of geophysical instruments as well. So, bear with me, I'm just trying to get my... Okay, so the arrows here show the different rock samples collected in these different parts of the Taurus Littré Valley by the Apollo 17 astronauts. The one at the top here shows the famous Apollo 17 orange soil, and it was visibly orange to the astronauts, which was a surprise because most of the lunar surface is grey, various shades of grey. This outcrop of orange soil occurred at the tip of this arrow here, where there's a little dark spot, and it represents a 100-meter diameter impact crater, which was nicknamed Shorty Crater. But anyway, this material was sampled, of course, and if you brought back to the Earth and then studied through a microscope, so this is a white light microscope image of the Apollo 17 orange soil. And it turns out to be these orange and black glass beads, which have been produced by a fire fountain type eruption, similar to that we see in Hawaii or Iceland, where the magma is erupted and it fragments into little pieces, and then it cools so quickly that it typically doesn't have time to crystallize, and so it forms these natural geological glasses, which are tinted orange in this case because of the titanium content of the magma. So anyway, I just show this is about 1 millimeter across, this microscope slide for scale, and it shows you what the Apollo 17 orange soil is made out of. Here is it shows, note the age, 3.6 gigayears, so 3.6 billion years old. Here is a piece of basaltic basalt, which was collected close to the Apollo lunar module. This is it in the receiving laboratory. If you go into the ESA's Astrometric Materials website, of course, you'll find all of these samples, so you'll be able to browse them to your heart's content. Put this on a microscope, and this is again, it's a white light microscope, and you can about 4 millimeters across. And the different shapes here are the different minerals that the rock is made out of. So this particular rock, in common with many lunar basalts, is dominated by 3 minerals, which are the 3 different shades of pinky grey you can see in this image. The white mineral here is plagioclase feldspar, and the pinky mineral is pyroxene, which is an iron magnesium bearing silicate. And the black minerals are ilmenite, so titanium iron oxide. Geological microscopes, whether used on the Earth or on the Moon or on meteorites or anywhere else, are usually able to put a polarizing filter into the light path. And if you look at rocks through cross-polarized filters, then the different minerals become different colors. So the rock then becomes like a stained glass window, where the different colors are enable one to identify the different minerals present. Anyway, I just show this slide to show the geological diversity at the Apollo, just at this one valley at the Apollo 17 landing site, and all the Apollo landing sites have obviously produced different samples of different types, but all collectively, this is the material that's helping us reconstruct the geological history of the Moon. So I said I would say something about the cratering rate on the Moon, which I said was one of the important scientific legacies of Apollo. And I want to draw your diagram to this graph, which shows the number of craters in a given area versus the surface age in billions of years, is one of the arguably one of the scientifically most important legacies of the Apollo program, and supplemented by the Lunar and Changi 5 programs. But in order to produce a graph like this, which shows the number of craters on a planet's surface as a function of the surface age, you need to be able to do 2 things. You need to find surfaces which have different numbers of craters, like this image at the top. It's clear that the left-hand part of this image has fewer craters than the right-hand part. Immediately, that tells us that the surface to the left is much younger because it's collected fewer impact craters since it was being exposed on the surface. But if we want to plot a graph like this, we also need to know how old these surfaces actually are. And there's no royal road to doing that. It's necessary to go and collect samples and then date these samples in a laboratory on the Earth by measuring the relative amounts of radioactive elements to the products into which they decay. It's called radiometric dating. And this will give you the ages of the rock. But it can only be done currently. It can only be done in large laboratories on the Earth, which requires samples to be obtained. But if you sample enough locations on the lunar surface, then you can date these rocks. And if you've collected them from surfaces where we've also counted the number of craters, then it becomes possible to plot this diagram. And so this is the lunar cratering, the number of craters as a function of surface age derived from the yellow rectangles show Apollo data points. And you can see the number of the cratering rate on the moon was falling very rapidly in the earliest history of the solar system, between 3.5 and 4 billion years ago. And then from about 3 billion years ago onwards, the impact cratering rate has decreased a lot. Which is fortunate for us, because if we were to extrapolate this to 0 billion years ago, this is our current impact cratering rate in the Earth-Moon system. That would be our impact hazard. So it's quite important to have figure out this impact rate. But from a planetary scientist point of view, it's hugely valuable, because it means that we can, having got this graph, it means we can now look at other parts of the moon where we have not visited yet, and therefore we have not collected any samples, but we can count the craters. So you could find an unknown bit of the moon's surface whose age you wanted to know, count the number of craters per square kilometer or whatever, and then go to this graph and read off the number of craters and then derive the age from the number of craters. But you can only do this once you've collected some samples from enough places to actually plot the diagram in the first place. And that's why one of the reasons scientifically the Apollo samples have been so important. And I just want to draw your attention to this blue square. This is where the age of the Changi 5 basalts that were returned to the Earth in December 2020. And they've turned out to be very important. It's only one spacecraft going to one location, but it's very reassuring that this blue square does sit on this green line. And therefore, it's kind of confirmed the cratering rate derived from the Apollo missions. I mean, it would have been very worrying to most lunar to planetary scientists had these Changi 5 points been sitting up here. I mean, that would have been an interesting discovery, but it would have cast our whole chronology for impact cratering in the inner solar system into confusion. So the fact that the Changi 5 samples are consistent with the Apollo samples in this respect is very, very reassuring. Treasures in the regolith. So this shows Buzz Aldrin's boot. So this is from Apollo 11. It's a nice image that shows the sort of consistency of the lunar regolith, the lunar soils. But to return to the point I made earlier, because the moon has no atmosphere, and for most of its history, the moon has had no magnetic field, the lunar soils like this are totally exposed to the space environment, which means they're impacted by the solar wind, and therefore we can extract those solar wind particles if we collect the soil samples, and this tells us about the flux of the solar wind through time. They're exposed to cosmic rays that come in from the galaxy, from exploding stars and other highly energetic astrophysical processes. And then we can extract the products of those cosmic ray interactions with the lunar soils and learn something about the solar system's past locations in the galaxy. And then just speculatively, we haven't found one yet, but I've written here meteorites from the early Earth. Just as we have on the Earth meteorites from the moon and Mars, it is pretty certain that there will be on the moon meteorites derived from the early Earth. And that is important because the early Earth, say the Earth in its first 500 million years of the Earth's history, we don't have any samples of the early Earth from the Earth itself because the Earth has destroyed them all or buried them all. So strangely, that if we wanted to find samples of the Earth's crust from, say, 4 billion years ago, or 4.4 billion years ago, or something like that, which is a very important time in Earth's history because it's the time when life was getting established on our planet, it's conceivable that the only place we might find such samples of the early Earth is on the moon. So, for example, here is a rock sort of near Buzz Aldrin's boot. This will be a moon rock. But there will be places on the moon where rocks like that might be meteorites derived from that have landed on the moon from the early Earth. And if we could find them, they would be a tremendously valuable set of samples, providing insights into the earliest history of the evolution of the Earth's crust. And finding them will be hard work because they're going to be very rare and very difficult to find. And so that would also become an argument for returning to the moon to obtain many more samples than we have currently done. Then there's the origin of the moon. So our current best favorite theory for the origin of the moon is the so-called giant impact hypothesis. But it's important to realize that this is a post-Apollo hypothesis. Before the Apollo samples were analyzed, there were several competing theories for the origin of the moon. And the scientific community has largely converged on this one, which is sort of shown schematically at the bottom of this picture, which posits that the early Earth was struck about a long time ago, about 4.5 billion years ago. But having formed the Earth, having just formed, is thought to have been hit by a Mars-sized, so very large, Mars-sized planetoid in the early solar system. And this giant collision will have created a disk of debris around the Earth. And the disk of debris will be derived from the uppermost mantle of the Earth, but also the mantle of the impacting object that is sometimes called Theia. And then the theory is that the moon condensed from this disk of debris orbiting the early Earth, which would be a mixture of Earth mantle and Theia materials. And this hypothesis for the origin of the moon, the giant impact theory, really became established after the analysis of the Apollo samples. I mean, there's a long story here. It would be a lecture in itself, but basically by comparing the similarity and the differences between lunar materials and the Earth materials, particularly in terms of the distant concentrations of volatile elements, and then combined with knowledge of the moon's bulk density, which is much less than the Earth, this giant impact theory gained credence. It's not a proven theory. I mean, the study of the lunar samples has provided some slight flies in the ointment for the giant impact theory. Actually, it's still very much an ongoing topic of research. But I think it's important to realize that our current best theory for the origin of the Earth's moon is derived from our study of the Apollo samples. And in any case, trying to prove it or disprove it as a mechanism for the origin of the moon will require going back to the moon to obtain a wider range of samples, especially samples of the moon's mantle, if we could find any. And I think we kind of know where we might go and look. There are none in the Apollo collection, but there probably are places on the moon where we could go to obtain samples of the moon's mantle that would tell us more. So this is my final slide. All of these are excellent reasons, scientific reasons for going back to the moon. I mean, the Apollo samples coupled with the Russian lunar samples and the Chinese Chang'e 5 samples, they've told us an awful lot, tremendously rich scientific legacy in these rocks. But they've also told us, made us realize there's a lot we don't understand, and that obtaining more information about the origin and evolution of the moon and the Earth-Moon system, and through that the solar system, probably will require us going back to the moon to collect rock samples from a wider range of places. And so it's very exciting in that context that that NASA is proposing to return people to the moon later this decade as part of the Artemis program. Okay, thank you very much. I think I will finish there.
That's great. Thank you very much, Ian. I'm not sure if I can be heard. Okay. Yeah, thank you so much, Ian. So much to take in there. We can now go to the Q&A, which I believe Arthur is going to chair. So he will try and have a look at the questions that have come through on the chat or the Q&A button. So we have a few minutes to go through questions. Are you there, Arthur?
Yes, I'm here. Yeah. Yeah. Very excellent presentations. Very, very interesting. And Erika, also the combination of your art and the science is fantastic. And Ian, I was fascinated also by your comments about the origin of the moon, because there is a friend of mine, William K. Hartman, who wrote the Origin of the Moon book. So I know the theory has been still disputed, but it's still, I think, the prevalent theory about the origin of the moon. So he would actually be a good candidate for a future webinar, because not only is he's a prominent planetary scientist, he's also an artist. So that gives it another cultural dimension to this whole thing. Well, in the Q&A session, we only have one question so far, and could Erika and Ian, could you provide links to the material that you showed, like to this NASA website? If you could put that in the chat, and we could stick it in, and the people can look at it in the thing, that would be great.
It would be good if later we could include that on the lunarology.space site as well, so people could look for some of these things there.
Yeah, we could put it on the webinar page. Now that would be great. So I don't see any other questions right now. Just the moon is so fascinating. You see in the back of my picture here, I'm really focused on the moon myself. So it's just, I mean, humanity's got to go to the moon. I mean, it's what Erika said. If God wanted man to be a spacefaring species, he would have given us a moon, and voila, we have it, you know. And without the moon, we wouldn't be here. The moon has, you know, it has slowed the rotation of the Earth. It's caused the tides. It's actually responsible for the origin of life on Earth and maintaining it. So without the moon, there wouldn't be much going on. And we have that in our white paper on our lunarology.space website. We have a little text about the origin of the moon and the impact, the influence of the moon on life on Earth. It's very interesting. So we have some more here. We have links down here. Yes, Erika?
Yeah, I just put the Astromaterials 3D link in the chat. If you can't see it for some reason, the best way to find Astromaterials 3D is just to Google Astromaterials 3D. It's the first thing that comes up. As you'll see in the link, it's quite a long address. So I always tell people just Google it. I'd love to share something actually in conversation with Ian, because there was, in thinking about meteorites on the moon that are fragments of Earth, there is actually there's new science. I don't know if it's been confirmed, but there is new science that has suggested that lunar sample 14321, which was from the Apollo 14 mission, has indicated that there is a small fragment of the Earth, what they think is the Earth, inside of that rock. And so that is one of the samples that's actually on the Astromaterials 3D website. So you can go to the Apollo 14 section and pull up that rock and look at it. The piece of the Earth is probably not in our piece of it, but I just wanted to make that comment that there is research. People are looking for pieces of the Earth in the Apollo samples.
Fantastic.
Yes, I know. I think that particular Apollo 14 sample, I mean, it'd be fair to say it's pretty controversial. I know it was originally, I mean, there are arguments for and against it being a part of the Earth, but yeah. But it is a bit controversial. But on the other, but it would be astonishing. I mean, the Apollo there are only 382 kilograms of Apollo rocks. It would really be astonishing if we'd found a bit of the Earth in the existing Apollo collection. I mean, but that's not a reason for not looking. We should look. But my suspicion is that I'm sure this stuff does exist on the moon. It's difficult to see how it cannot exist on the moon. So whether it's in this Apollo 14 sample or not, it's going to be somewhere, and so looking for it is a high, to my mind anyway, one of the high scientific priorities of going back to the moon to look for early Earth material.
So we have one.
I have a question, if I can insert one very quickly. This is for Erika. Just in your presentation, just looking at how closely you worked physically closely with these samples over time. It seems that your relationship and sort of even feelings towards the moon may have kind of evolved over the last several years. Are there any moments or experiences you can share with us about things that you found or insights?
Yes, I mean, I feel tremendously privileged to be able to have spent as much time as I have. You know, I think I calculated it one time, and it was well over several thousand hours that I've spent with the samples, and that's really unusual. But it was also required because of the deep looking that I was doing to image the samples and to capture the imagery, and it was a slow process evolving those procedures and getting the image data. But my relationship with the rocks is really, really evolved. And I have to say that it's something that I've spent a lot of time thinking about. In fact, I'm been writing about it, and it will eventually become part of a publication that I'm working on. But I think the story that really struck me was this experience of that I sort of alluded to in that last rock, the Pharaoh and Anorthosite, that I shared with you, the sort of origin story of that rock and others in the collection that are anorthositic were very difficult to photograph, and partially because I'm illuminating them through glass, and I'm shooting through glass, so there's a lot that's troublesome, and also because of the construction of the nitrogen cabinet. I only have one location that I can actually put a lunar a light to in the lunar cabinet, and that's from above. So, photographing with the light at a high altitude is always very troublesome. So I was constantly navigating, having really bright highlights in certain areas of the rock. And when I was imaging 60025 and others like it, I started to realize that, I kept having to turn the light down a little bit, and then I try to image it, and it was just, the whites were so bright. And slowly through this process of finding the right illumination for the rock, for the imaging, I was spending time looking at the characteristics, physical characteristics, the spectral characteristics of those minerals, of that mineral in particular, that creates that luminance that we see when we see the moon at night. And there's this bright glow in these darker areas, and it's those brighter glowing areas that are so embedded with this anorthositic material. And it's hard to describe, but there aren't many opportunities. Even my colleagues who work with the samples in the lab under illumination, they're not using the same illumination that I am. They're using laboratory illumination that's much more general and overhead, where I was using a very particular kind of illumination that was really spotlit on the sample. So there was this experience that I had where I really I felt like I learned viscerally from the moon itself. It was teaching me why it glows the way it does in the night sky, and that relationship is something that profoundly impacted me.
I can imagine.
We have a couple more questions from the Q&A, and the last one sort of relates to what you just said, Erika. I mean, we saw this case with the gloves that go in. I mean, did you actually touch the rocks, or could anybody do that, or is there the tactile quality of the rocks? Can that be ascertained anyway?
Not really. I mean, not. Yeah, so the rocks are, if you're handling the rocks, you're handling them, through the nitrogen cabinet gloves. And then if you have to actually handle the rocks, you have additional gloves that go on top of those gloves that are made of Teflon so that they're really, really protected. The processors who were doing the handling of the rocks to put them on the rotation stage for me, which they sit on Teflon pads, all of that was very choreographed. And the only time that I was really handling the rocks was when I was CT scanning them. And at that point, they're inside of a triple bagged, they're bagged with Teflon 3 times, and that's filled with nitrogen. So you're handling a packet. So I have held them in that configuration. And in that sense, you can see details a lot more close up, which I love. And also you can get a sense of the weight. For example, the anorthositic rocks are obviously very, very light. I mean, almost like featherweight compared to the basalts, as you might expect. But feeling that and, really feeling the weight of the moon, if you will, was really impactful.
And another question we had a little bit earlier was, are there any international protocols for sharing moon rocks and other data?
Yes. I mean, as far as the NASA protocols are concerned, for scientific purposes, then it's a completely open process. So investigators just apply to a peer review committee, and then the request is judged favorably or not. And if it's just favorably, then an allocation is made. I think there are in the international coordination of lunar exploration is a really important topic, and it's going to get more important in the future. I think currently there exists an international coordinating body called the International Space Exploration Coordination Group, ISEG, which is a grouping of currently all of the world's space agencies, including China, which is important. Where they're trying to coordinate future human activities in exploring the solar system at an international level. It's not as robust as many of us would like. There's a lot to do in developing the international rules and coordination frameworks for lunar exploration. So there is something, but there could be more.
Can I ask Ian a question, please? I read your article where you supported the idea of a world government that should manage the next space exploration in a fair and peaceful way. Of course, I like the idea. I think that it would be very, very important. But don't you think that this idea in these times that are so violent and messy, it's a little bit utopian? But still, if we have to continue to fight for this idea, where do you think we should start?
Well, that's an excellent question. It interests me a lot. I mean, I have written on this topic. I'm not sure whether it's a topic Lisa was expecting to have raised tonight in the context of moon rocks. I mean, I'm probably so. I think we have to start. We are where we are. We have to start where we are. So I think the task for the coming decades is to strengthen what international organizations we've got through ISEG and other international fora, through the United Nations. We should be doing that anyway. Now, it's true that in the longer term, I am a world federalist. I think the world needs a government to solve planetary level issues. a federal organization that enables decisions to be made close to where they're needed to be made. So a kind of federal structure. But that currently is a very long-term aspiration. I agree with you. So yes, it is utopian at the moment. I would just say though that the world needs a global coordinating political framework for many things. Space exploration is only one. We need a global coordinating framework to manage and prevent climate change and biodiversity loss, and to enforce nuclear disarmament, and to try and level up the world economy so that it's not as unequal as it is at present, and to manage international mega international or commercial entities. So I think there are good reasons for having stronger, effective global governance for all of these things, quite irrespective of space exploration. But then if a global political structure has to evolve to deal with all of these other problems, then yes, it seems to me that space exploration would fit naturally within its remit, because space is a transnational domain. I mean, exporting nationalisms from the planet Earth into space is nonsensical. Space is a transnational domain, and so we should be looking for transnational means of organizing human activities. That's what I think, but I have a feeling we may be getting off the topic of moon rocks and into politics.
A bit, yes. And I would like also to tell Erika that I like very much the multidisciplinary approach that she takes in her artistic work. It's very, very important that to bring together art, science, nature, and the cosmos, and then our knowledge of cosmos. And I think that we should learn from that experience that we should mingle more often science, technology, and spirituality, let's say. Probably we will if we use a humanistic approach, also in the whatever concerns let's say exploration, space exploration, I think that we could tackle best the psychological, sociological, and the spiritual problems that are connected to space exploration, to the enormous leaps forward that the science and technology have made.
Yes, thank you. I fully agree with you, and I think that more and more there's a need for the arts and the sciences and technology to be in this conversation. I think the arts have always reminded us of our humanity, and also facilitated empathy, because it's about having an experience with the world. And there's more links between art and science than there are differences, but the differences are also important. And really sourcing meaning and finding like empathetic relationships with our natural world, I think, could bring a lot to the issues that we are struggling with. So thank you.
I agree.
Thank you.
Can I raise a question? Because I was having my hands up some time. So no. So first of all, again, thank you to all of you, and I think this was very interesting. And this was an example of merging, as Remo said. By the way, the Moon Village exploration is exactly that. That's why we have so many different groups, and that's why we urge also the co-chair of the different working group to merge with each other and to also do some cross working group, which include together, let's say, science as well as art and many other things. So that is the first remark, which goes exactly in the direction which you all said. So it's an encouragement, maybe also for next year. The other is a piece of information, and then the third is a question. The piece of information, we just have recently initiated a new working group, which is called Lunar Physiology and Psychology. It's a brand new working group, which is led by a doctor from Brazil, which is living actually in UK. You can find information on the website. So psychology is also an important aspect that they will be dwelling. So maybe, again, next year, you might want to try to do something together with them. And then my question is coming back to the rock. Nobody spoke about the smell. And being a very practical person, I think we all heard about in the past about this burning smell of the rocks. And of course, maybe if anyone can comment about there is any, because when you look at an object, you see a picture, but the smell is a much more, I would say, immediate type of impact on humans, at least the way I think. So could you comment, because that is something which might be of also interest for the general public. Thank you again for the great presentation. Thanks.
Thank you. I can actually comment on that. I had an opportunity, an artist visited NASA Johnson Space Center was interested in cultivating a scent of the lunar, the Apollo samples for a fashion line that he was working on. And so since I work at the intersection of art and science, the PAO invited me to be a part of this situation. And it was great to meet the artist and have this opportunity. So we were allowed to smell a small return sample. So it was a sample of lunar soil that had been sent out for study and had returned. So it was no longer pristine. And we were allowed to smell the sample. And I have a really strong sense of smell. And so the best way that I have been able to describe it is it's this combination. So I lived in the desert for a long time in the southwest of the US. And if you if you've ever been in a situation where you're out in like really, 100-degree heat in the desert and the sunlight is hitting, basalt, and there's this effervescent smell, and it's very, I don't know what to call it, but it smells exactly like sunlight hitting basalt on the one hand, and on the other hand, like metal being lathed. And it was, to my nose, it was those two combination. Ian, have you ever smelled?
I haven't, although it's interesting that you've had someone trying to artificially make the scent, because we had a student, Marina Barcinella at Birkbeck a couple of years ago. She's now doing a PhD in astrobiology, and she was a perfumist, and maybe still is, now becoming an astrobiologist. She too had this idea and was trying to make moon rock scents for perfume. It's interesting. I may try and put her in touch with you, because it seems that other people are having the same idea. I personally haven't smelt any moon rocks, so I can't comment. Remo, I should just stress that I personally am going to have to leave at 6 UK time, which is in 9 minutes, because I have another meeting I have to go to, just to advise.
I will just say one last thing on the note of smell, which is that the astronauts themselves described the scent as gunmetal, which I didn't experience myself when I smelled that sample, but that was very clearly they were consistently indicating that that's what it smelled like to them.
Fantastic. So I suppose we should wind this up. We could talk on and on, I think. just to let everybody know that this recording will be available on the lunarology.space website in the events and webinar areas. So if you've missed this and you want to go back through it, it'll be a few days before we get it up there. And also consider joining the Moon Village Association, and one of the groups, the Cultural Considerations group, is always looking for good ideas, things that we want to pull together to touch on the cultural aspects of the moon. So we're happy to have people come to our open meetings. There's actually a oh gosh, what's it called? A chat group. It's Slack. We're on Slack, so you can find us there as well. But send inquiries through the lunarology.space website if you'd like. Anyway, I just wanted to thank both Erika and Ian for putting together these sort of very careful, thoughtful presentations, and giving us lots to think about on the next stages when we do actually go back to the moon. All the things that we ought to be thinking about, or the new possibilities that it proposes. So anyway, thank you very much, everyone, and
thank you.
We'll let you know next time when the next one is.
Yeah,
Okay.
thank you. Thank you,
Thank you, everybody.
Bye. Bye.